Our project is radar. We mount cameras and 4D radars on roadside infrastructure and fuse them together to detect vehicles, pedestrians, and road structure in real time. Cameras give us the visual detail, radar gives us depth and speed even in bad weather, and together the system can warn any vehicle in range. The image encoder is what processes the camera feed. It pulls out the visual features that the rest of the pipeline depend on. A stronger encoder means better perception overall, so choosing the right one was critical. We tested 4 encoders: ResNet 101, ComNext-B, SegFormer, and SwinB. All used the same segmentation head UPerNet and were trained under identical conditions on the new images mini dataset. SegFormer scored the highest at 0.57 mean IOU, followed by ComNext at 0.54, ResNet at 0.50, and SwinB at 0.43. Despite being the lightest model, SegFormer outperformed the heavier architectures. Our next steps are that we'll validate on the full 92,000 image new images dataset, fine-tune SegFormer for our infrastructure camera views, and begin integrating it with the bird's eye view transformation stage of our pipeline.
And my role is of a radar encoder. I process raw radar point clouds and extract spatial and velocity features so the fusion system can combine that with the camera data. In this quarter, I built a point and classifier that hit 88.5 accuracy on V2X radar dataset and completed a point velocity detection pipeline adapted for 4D radar. Got it working end to end. You can see the actual output results on my side, which are the green are the predictions and the red is the ground truth. The MAP is 0.66, but that's only 3% data set. Published result was on 7,000 samples, and scaling up and building a novel radar encoder from scratch is what I'm focused on this quarter. Thank you.
Good morning, I'm Ruthvik. I'm part of the Radar Camera Fusion project. As you can see in this picture, we process the camera image, the radar image, fuse it together for object detection. I primarily focused on the radar-only pipeline, and where I experimented with different encoders and decoders of radar data and trained it on the New Scenes Mini dataset. So the encoder pipeline is where we pre-process the raw radar data, map it to a 128 times 128 grid, do some more processing, and then pass it through a ResNet for object detection. And these are the decoders we use for detection. The results with the center point detection head with the 20% confidence is we have some more extra guesses, but with the 50% confidence, the guesses we have are pretty exact to the ground truth values. This is trained on 50 epochs on the mini dataset, but with transformer model, everything is pretty random and pretty much wrong. This is because the radar data is sparse and the transformer is just guessing. So for next steps, we plan to train it on the full dataset and fuse both the pipelines together.
Hi, my name is Adolfo Ramos, and here's a figure of point cloud convolution, which takes an input point cloud made up of coordinates and feature vectors and creates an output point cloud. It has a heavy reliance on maps, which are data structures representing spatial relations between input, output, and weights, and help identify where non-zero data exists. Due to the sparsity of input point clouds, there are irregular memory access and a high number of sequential coordinate comparisons, which lead to high latency, taking up 60 to 90% of runtime. The proposed architecture is made up of the mapping core, which uses 3 content addressable memory buffers,